Now, in this lecture, we will prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides of the triangle to its CVN. So here we have triangle ABC. Side AB of triangle ABC equals to C units in its length, side AC equals to B units in its length, and side BC equals to A units in its length, and the CVN in this triangle ABC is line segment AD. Again, the CVN is line segment AD, and Stewart's theorem yields a relation between the lengths of the sides of the triangle to its CVN. The CVN is AD. And according to Stewart's theorem, the following equation is true, that B squared times n plus C squared times n equals to A, and we will open brackets. Inside the brackets we have D squared, the length of the CVN square, plus m times n. Again, according to Stewart's theorem, the following equation is true, that b squared times m plus c squared times n equals to a. We open brackets. Inside the brackets we have d squared plus m times n. So we have to prove that this equation is true. Okay, so we start with the first method. In the first method, we will do a construction, that is to say, from the vertex A, we will go perpendicular on side BC. Again, from vertex A, we will go perpendicular on side BC. So this angle equals to 90 degrees, and this angle, it is also equal to 90 degrees according to our construction. Okay, we will define the touching point of the perpendicular from point A and BC as E. This point E. In addition, we will define the length of line segment ED, this line segment ED, as X we will define the length of the perpendicular AE as H. AE equals to H according to our definition. And from the drawing, we can see that the length of line segment BE equals to BD over ED. Again, BD over ED equals to BE. I'll write it down. The length of this line segment BE is equal to BD minus ED. BD minus ED. Repeat again. The length of line segment BE equals to BD minus ED. So BE, this line segment BE equals to BD. BD equals to M units in its length, so we substitute BD by M minus ED. ED equals to X units in its length, so we substitute ED by X. In conclusion, we found out that the length of line segment BE equals to M minus X. Okay, BE equals to M minus X, so I write it down. Here, BE equals to M minus X units. Okay. And from the drawing, it is very easy to see that the length of line segment EC equals to ED plus DC. Again, ED plus DC equals to EC. That is to say, EC equals to X plus N units. In the line segment BE, this line segment equals to M minus X units in its length. Okay, again, BE equals to M minus X units in its length, and line segment EC equals to X plus N units in its length. Okay. In the next step, we'll implement the Pythagoras theorem in the green right triangle, triangle AED. In the green right triangle, triangle AED. Here by PT is abbreviation for Pythagoras theorem. According to Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, in the right green triangle AED, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right green triangle AED is AD, therefore the square of the hypotenuse is AD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to ED squared plus AE squared. Repeat again. In the right green triangle, triangle AED, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle, the right green triangle AED, AD squared equals to ED squared plus AE squared. Okay. So here, the hypotenuse AD equals to D units in its length, therefore the square of the hypotenuse is D squared, and must be equal to ED squared. ED is X, therefore ED squared is X squared plus AE squared. AE equals to H units in its length, therefore A squared is H squared. In conclusion, I found out that according to the Pythagoras theorem, in the right green triangle AED, d square equals to x square plus h square. Okay? This is the first equation. In the next step, we'll focus on the right green triangle, triangle AEC. On the right green triangle, we will implement the Pythagoras theorem on the right green triangle, triangle AEC. On the right triangle, triangle AEC. It is green partially. So in the right green triangle AEC, by PT is a measure for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 1. The square of the hypotenuse in the right triangle AC is AC. Therefore, the hypotenuse in the right triangle AC is AC. Therefore, the square of the hypotenuse is AC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AE squared plus EC squared. I'll repeat again. In the right triangle AEC, according to the Pythagoras theorem, AC squared equals to AE squared plus EC squared. This is equation number 1. So AC is B, or the length of side AC is B units. So we substitute AC by B, therefore AC squared is B squared and is equal to AE squared. AE equals to H units in its length. AE equals to H, therefore AE squared is H squared plus EC squared. We have already found out that the length of side EC is equal to x plus n. Therefore, EC squared is x plus n squared. So, according to the Pythagoras theorem, in the right triangle AEC, B squared equals to h squared plus x plus n squared. Here we'll open the brackets of this equation, equation number 1, and we'll get that according to equation number 1, B squared equals to h squared, x plus n squared equals to x squared plus n squared plus 2 times xn. Okay. So in this equation, equation number 1, we have h squared plus x squared. And according to what we have already found out, that h squared plus h squared equals to d squared, so we can substitute h squared plus x squared by d squared. So we do it now and we'll get that according to equation number 1, b squared equals to h squared plus x squared, h squared plus x squared, and we already found out that x squared plus x squared equals to d squared, so we substitute h squared plus x squared by d squared plus n squared plus 2 times x times n. So this is actually equation number 1. B squared equals to d squared, again, b squared equals to d squared plus n squared plus 2xn. In the next step, we will focus on the right triangle ABE. Again, we will focus on the right pink triangle ABE, and we will implement the Pythagoras theorem on this right pink triangle ABE. Okay. So, in the right pink triangle ABE, by PT, triangle ABE is the right pink triangle. So by PT, this will be equation number 2. By PT, we get that AB square, the hypotenuse is AB, the square of the hypotenuse is AB square, equals to AE square plus BE square. I repeat again. In the right pink triangle ABE, according to the Pythagoras theorem, we get that AB square equals to AE square plus BE square. So AB equals to C, therefore AB square is C square, and it is equal to AE square. AE is edge, therefore AE square is edge square plus BE square. BE, we have already found out that B equals to M minus X, therefore BE square equals to M minus X square. So, in conclusion, according to the Pythagoras theorem, in the right pink triangle ABE, we found out that C square equals to H square plus M minus X square. So here we open the brackets on this equation number 2, on this side of the equation, and we get that C square equals to H square plus M minus X square equals to M square plus X square minus 2 times MX. So again, in equation number 2, we have the expression H square plus X square, or X square plus H square, and we already found out that X square plus H square equals to D square. So we substitute H square plus X square in this equation number 2 by D square. And we'll get that according to equation number 2, C square equals to H square plus X square is D square. So we substitute H square plus H square plus X square by D square plus M square minus 2mx. Repeat again, according to equation number 2, in the right triangle ABE, we found out that C square equals to D square plus M square minus 2 times mx. In the next step, we'll create equation number 3. Equation number 3 is equal to the multiplication of equation number 1 by x, the multiplication of equation number 1 by m, the multiplication of this equation number 2 by n, so it is equation number 2 times n, and then we will add the two equations with each other. This will give us equation number 3. Again, equation number 3 is the multiplication of equation number 1 by m plus and then the multiplication of equation number 2 by n, and then the addition of the two equations 1 and 2 with each other. Okay, so here we'll start with the right side of each equation, of equation number 1 and the right side of equation number 2. So first of all, we will multiply the right side of this equation number 1 by m. So it is m. In the right side we have d squared plus n squared plus 2 times xn. And then we will multiply also the right side of equation number 2 by n, so it is n. In the right side of this equation number 2, we have d squared plus m squared minus 2 times mx. So we multiplied the right side of equation number 1 by m. Then we multiplied the right side of equation number 2 by n, and then we add the two right sides of equation number 1 and 2 with each other, and it is equal. In the next step, we will multiply the left side of equation number 1 by m. That is to say, it is m times b squared, plus we will multiply the right side of equation number 2 by m, that is to say it is n times c squared, and then we will add the two sides together. We will add the two left sides of equation number 1 and 2 with each other. Okay? That is to say it is mb squared plus nc squared. Okay? In the next step, we'll open the brackets on both sides of this equation number 3. And we'll get that according to equation number 3, m times d squared is md squared plus m times n squared is mn squared plus m times 2xn is 2 times 2xmn plus n times d squared is nd squared plus n times m squared is mm squared and plus n times minus 2mx is minus 2mnx. Okay? And in the left side of equation number 3 we have p squared times m plus c squared times n. So this is actually equation number 3 after we open the brackets on both sides of the equation. Okay? In the next step, we will take out a common factor of d squared from this expression and from this expression. Okay? So md squared, when we take the common factor of d squared from md squared, inside the brackets what is left is m, and when we take out the common factor of d squared from nd squared, what is left inside the bracket is n. Okay? In the next step, we will take out a common factor of m times n from this expression. So what is left from this expression? First of all, we have here we have 2x minus 2mx times n is minus 2mxn. So here we have 2xmn minus 2mxn. Those two expressions are equal to each other, therefore they will get cancelled. 2xmn minus 2xmn equals to 0. So those two expressions will get cancelled. So in the next step, we take out a common factor from this, a common factor of mn from mn squared. What is left from this expression after we took from it m times n as a common factor? What is left is actually n. And what is left from this expression m squared after we took from it nm as a common factor? What is left is actually m. So inside the brackets we have m plus n. Okay? And it is equals to b squared times m plus c squared times n. In the next step, we take out a common factor m plus n from those two expressions. Okay? And we will get that, so m plus n is a common factor. What is left from this square times m plus n after we took from it m plus n as a common factor? What is left is actually d squared. And what is left from this expression m plus n after we took from it mn as a common factor? What is left? Again, what is left from this expression mn times m plus n after we took from it m plus n as a common factor? What is left? It is actually mn. And it is equals to b squared m plus c squared n. What is m plus n? What is m plus n? From the drawing, it is very easy to see that m plus n equals to a. Okay? The length of side BC is a, and side BC equals also to m plus n, that is to say m plus n equals to a, so we can substitute m plus n by a. Okay? So we found out that m plus n equals to a, and therefore we substitute m plus n by a in this equation, equation number 3, and we will get it according to equation number 3. M plus n is a, so it is a d squared plus mn equals to b squared m plus c squared n. Okay, and here we have Stewart's theorem, and Stewart's theorem here it is b squared m plus c squared n equals to a. Inside the brackets we have d squared plus m times n. Repeat again. We actually proved the Stewart theorem. Why? Because according to Stewart's theorem, in any triangle, b squared m plus c squared n equals to a. Inside the brackets we have d squared plus m times n. Exactly like this equation, b squared m plus c squared n equals to a. Inside the brackets we have d squared plus m times n. Okay, we succeeded to prove Stewart's theorem according to the first method. In the next step, we'll prove Stewart's theorem according to the second method. I repeat again, according to Stewart's theorem, b squared times m plus c squared times n equals to a, and we open brackets. Inside the brackets we have d squared plus m times n. Okay, and here we will define angle ADB as theta. We know that BC is one side of triangle ABC, therefore it is absolutely a straight line. And we have rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line BC at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of BC at point D? We have this angle that is theta, plus the missing angle, that is angle ADC total, they must be equal to 180 degrees according to rule number 1. So the missing angle must be equal to 180 degrees minus theta. Repeat again, the missing angle, angle ADC, must be equal to 180 degrees minus theta in order to complete the sum of the angles on the upper side of BC at point D to 180 degrees. Angle ADC must be equal to 180 degrees minus theta. Why? Because 180 degrees minus theta plus theta equals to 180 degrees. Exactly according to rule number 1. Okay? In the next step, we will implement the law of cosines in both triangles, triangle ADB and triangle ADC. Okay? We'll implement the law of cosines in the plane triangle ADC. So I remind you what is the law of cosines? The law of cosines is true in any triangle. So here we have triangle ABC that could be any triangle. Again, this is triangle ABC, it could be any triangle. And we know that the length of side AB is A unit, side AC equals to B units in its length, side BC equals to C units in its length, and angle BAC equals to theta. Then, according to the law of cosines, here I write down this is the law of cosines. C square equals to A square plus B square minus 2 times AB times cosine theta. Okay? If we will add 2 times AB cosine theta to this equation, then we will subtract C square from this equation, and then we will divide this equation by 2 times AB, and finally we will get that cosine theta equals to A square plus B square minus C square over 2 times AB. Okay? Again, this triangle ABC that could be any triangle, cosine theta equals to A square plus B square minus C square over 2 times A times B. We will implement the law of cosines in our green triangle, triangle ABD. According to the law of cosines, in the green triangle, triangle ABD, we will get that cosine theta, this is angle theta, cosine theta equals to m square plus d square minus c square over 2 times m times d. Repeat again, in the green triangle, triangle ABD, according to the law of cosines, we get that cosine theta, this is equation number 1, cosine theta equals to m square plus d square minus c square over 2 times md. In the next step, we'll implement the law of cosines in this pink triangle, triangle ADC. In the pink triangle, triangle ADC, according to the law of cosines, this will be equation number 2. Cosine 180 degrees minus theta. Here this angle equals to 180 degrees minus theta. So cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times dn. Repeat again. In the pink triangle ADC, according to the law of cosines, we get that cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times dn. According to the trigonometric identity, cosine 180 degrees minus theta equals to minus cosine theta. According to this trigonometric identity, we substitute cosine 180 degrees minus theta in this equation number 2, by minus cosine theta, and we'll get that minus cosine theta equals to d square plus n square minus b square over 2 times dn. This is equation number 2. In the next step, we will multiply this equation number 1, by minus 1. Okay, we will multiply it by minus 1, and we will get that cosine theta times minus 1 is minus cosine theta, and it is equals to minus, we multiply this side of the equation also by minus 1, so it is minus, we'll open brackets, m square plus d square minus c square over 2 times md. So actually, this is equation number 1 after we multiply it by minus 1. Okay? We have already found out that according to equation number 2, minus cosine theta equals to d square plus n square minus b square over 2 times dn. Okay? So those are the two equations, equation number 1 and equation number 2. In the next step, we'll create equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Okay? And so according to equation number 3, we found out that minus cosine theta according to equation number 1 is minus m square plus d square minus c square over 2 times md, and it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 is d square plus n square minus b square over 2 times dn. In the next step, we will multiply this equation number 3, by 2d, and we will get that according to equation number 3, so here we have 2d over 2d is 1, so 2d will get cancelled, and we left in the denominator only with m. Okay, so we have in the numerator minus m square plus d square minus c square over m, and it is equal, we multiplied this side of the equation also by 2d. 2d over 2d is 1, so 2d will get cancelled, So in the denominator on this side of the equation we left only with n. And in the numerator we have d squared plus n squared minus b squared. In the next step, we'll cross multiply this equation number 3, and we'll get that according to equation number 3, so it is n or minus n. Inside the brackets we have m squared plus d squared minus c squared, and it is equal to m. Inside the brackets we have d squared plus n squared minus b squared. So actually this is equation number 3 after we cross multiply it. In the next step, we'll open the brackets on both sides of this equation number 3, and we'll get that according to equation number 3, n minus n times m squared is minus n m squared, minus n times d squared is minus n d squared, and finally minus n times minus c squared equals to plus nc squared. Why? Because minus times minus is plus, and is equals to m times d squared is md squared, plus m times n squared is mn squared, m times minus b squared is minus mb squared. Okay, in the next step we will add nm squared and also nd squared to this equation, and we'll subtract nc squared from this equation and equation number 1. So in this side of the equation we have left with nothing. Why? Because we added nm squared and also nd squared to this equation, and we subtracted nc squared. So in this side of the equation we left with 0. If nothing, 0 equals to, here we have already in this side of the equation md squared plus mn squared minus mb squared, and then we added nm squared to this equation, so it is plus nm squared. We added nd squared to this equation, so it is plus nd squared, and we subtracted nc squared from this equation, so it is minus nc squared, and it is equals to 0. Okay. In the next step, we will take d squared as a common factor. We will take out d squared as a common factor from this expression and from this expression. So d squared was taken as a common factor. So what is left from having d squared after we took from it d squared as a common factor? What is left is actually m. What is left from nd squared after we took d squared after we took from it d squared as a common factor? What is left is actually n. So here we found out that d squared times m plus n. In the next step we'll take mn. We'll take out mn as a common factor from this expression and from this expression. So what is left from nm squared after we took from it nm as a common factor? What is left is actually m. And what is left from mn squared after we took from it mn as a common factor? What is left is actually n. We have also here minus mb squared minus nc squared. That is equal to 0. In the next step, we will add mb squared and nc squared to this equation, and we get that according to equation number 3, d squared m plus n plus mn times m plus n equals to b squared m plus c squared n. Here, from this side of the equation, we take out m plus n as a common factor from those two expressions. So m plus n is a common factor. What is left from this expression after we transform it m plus n is a common factor? What is left is actually d squared. And what is left from this expression after we transform it m plus n as a common factor? What is left is actually mn. And it is equals to b squared m plus c squared n. In the next step, we will substitute m plus n by a. We have already found out that m plus n equals to a. Okay, here m plus n equals to a. So substitute m plus n by a in this equation, equation number 3. And we get that m plus n is a. Inside the brackets we have d squared plus mn, that is equals to b squared m plus c squared n. In conclusion, we found out that b squared m plus c squared n equals to a. Inside the brackets we have d squared plus mn. Okay, and this is actually Stewart's theorem. As you can see here, b squared m plus c squared n equals to a. Inside the brackets we have d squared plus mn. So we succeeded to prove Stewart's theorem according to the second method. In the next step, I will summarize the lecture. We start, of course, with the first method. In this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides of the triangle and its civilian. The civilian here, this is triangle ABC, and the civilian of triangle ABC is line segment AD. Again, line segment AD is the civilian of triangle ABC, and Stewart's theorem, in a nutshell, yields a relation between the lengths of the sides of the triangle and its civilian AD. And according to Stewart's theorem, b squared times m plus c squared times n equals to a, open brackets, inside the brackets we have d squared plus m times n. Okay? So, in the first method, we did a construction from point A, we drew perpendicular on BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. We defined side ED as X, side AE equals to edge units in its length according to our definition. And finally, what is the length of side BE? The length of side BE equals to side BE equals to side to BD minus ED. Again, BD minus ED equals to side to BE, to the left of side BE. BD equals to M units, ED equals to X units, according to our definition. Therefore, BE equals to M minus X. Okay, and also from the drawing it is very easy to see that EC equals to X plus N. Okay, in the next step we implemented the Pythagoras theorem on the right triangle, triangle AED. According to the Pythagoras theorem, in the right triangle, triangle AED, AD square equals to AE square plus ED square. Repeat again. In the right triangle, triangle AED, AD square equals to ED square plus AE square. AD equals to D, therefore ED square is D square, and it must be equal to ED square. ED is X, therefore ED square is X square plus AE. AE equals to H according to our definition, therefore AE square is H square. In conclusion, we found out that in the right triangle AD, D square equals to X square plus H square. In the next step, we focused on the right triangle, triangle ABE, on the right triangle, triangle ABE. We actually focused on the right triangle, triangle AC, the big right triangle, triangle AC. We implemented Pythagoras theorem on the right triangle, triangle AC. According to the Pythagoras theorem, in this right triangle AC, AC square equals to AE square plus EC square. So in the right triangle, triangle AC, AC square equals to AE square plus EC square. AC equals to B units in its length, therefore AC square is B square, and it is equal to AE square. AE is H, therefore AE square is H square plus EC square. EC equals to X plus N, therefore EC square is X plus N square. Okay, so in conclusion, we found out that B square equals to H square plus X plus N square. Here we open the brackets on this side of equation number 1 and found out that B square equals to H square and X plus N square equals to X square plus N square plus 2 times Xn. We have already found out that X square plus H square equals to D square. So we substitute X square plus H square in this equation, equation number 1, by D square. And we got that B square equals to X square plus H square is D square plus N square plus 2 times Xn. And finally, we implemented the Pythagoras theorem on the right pin triangle, triangle AEB. On this right pin triangle, AB square equals to AE square plus BE square. Repeat again, in the right pin triangle, triangle AB, AB square equals to AE square plus BE square. AB equals to C units in its length, therefore AB square is C square, and it is equals to AE square. AE is H, therefore AE square is H square plus BE square. BE equals to M minus X, therefore BE square equals to M minus X square. Okay, so in conclusion, found out that C square equals to H square plus M minus X square. This is equation number 2. We opened the brackets on this side of equation number 2 and found out that C square equals to H square plus M minus X square is M square plus X square minus 2 times MX. We have already found out that X square plus H square equals to D square here. Therefore, we substituted X square plus H square in this equation, equation number 2, by D square, and found out that C square equals to H square plus X square is D square plus M square minus 2 times MX. Then we created equation number 3. Equation number 3 is the multiplication of equation number 1 by m, then the multiplication of equation number 2 by n, and then the addition of the two equations with each other. Okay, so we multiplied this side of equation number 1 by m. So it is m d squared plus n squared plus 2 times xn. Then we multiplied this side of equation number 2 by n. So it is n, and inside the brackets we have d squared plus m squared minus 2 times mx. And then we multiplied this side of equation number 1 by m. So it is mb squared, and we multiplied this side of equation number 2 by n. So it is nc squared. Okay. Then we open the brackets on both on this side of equation number 3, and we found out that according to equation number 3, we have this expression. Here we have 2 times xmn minus 2 times xmn is 0. So those two expressions will get cancelled. And then we took this square, we took out this square as a second factor from this expression and from this expression. So inside the brackets we left only with m plus n. Then we took common factor m times n from this expression and from this expression. So inside the brackets we left only with m times n, and it is equal to b square m plus c square n. Then we took m plus n as a common factor from those two expressions. So inside the brackets what is left from those two expressions is d square plus mn. That is equal to b square m plus c square n. N plus m equals to a. Here, n plus m equals to a. So we substitute n plus m by a, and found out here that m plus n is a. So it is a times d square plus mn equals to b square m plus c square n. Or so here b square m plus c square n equals to a. Inside the brackets we have d square plus mn, and this is exactly Stewart's theorem. So we proved Stewart's theorem according to the first method. In the next step we proved Stewart's theorem according to the second method. According to the second method, in the second method we defined angle ADB as theta, and therefore this angle, the adjacent angle angle ADC must be equal to 180 degrees minus theta. According to rule number 1, that the sum of the angles on one side of the straight line is equal to 180 degrees. And then we implemented the law of cosines in the green triangle and also in the pink triangle. In the green triangle ABD, and in the pink triangle ADC. The law of cosines is true in any triangle, so this triangle ABC could be any triangle. The length of side AB is A, side AC equals to B units in itself, and side BC equals to C units in itself. This angle BAC equals to theta. So in any triangle ABC could be any triangle. So in any triangle, C square equals to A square plus B square minus 2 times AB times cosine theta. Then, in a couple of operations, we get easily that cosine theta equals to A square plus B square minus C square over 2 times AB. So in any triangle, cosine theta equals to A square plus B square minus 2 times A square plus B. Again, cosine theta equals to A square plus B square minus C square over 2 times AB. It is true in any triangle. So we implemented the law of cosines in the green triangle ABD. In this green triangle ABD, according to the law of cosines, we'll get that cosine theta equals to b squared plus m squared minus c squared over 2 times b times m. Repeat again, in the green triangle ABD, cosine theta equals to m squared plus m squared plus d squared minus c squared over 2 times md. Okay, then we implemented the law of cosines in this spin triangle ADC. According to the law of cosines in this spin triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times nd. Repeat again, the big triangle ADC, cosine 180 degrees minus theta equals to d squared plus n squared minus b squared over 2 times dn. According to the algebraic to the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta, we can substitute cosine 180 degrees by minus cosine theta. We did it, and we got it according to equation number 2. Minus cosine theta equals to d squared plus n squared minus b squared over 2 times dn. Then we multiplied, in the next step, we multiplied this equation number 1 by minus 1. So here, cosine theta times minus 1 is minus cosine theta. And here, we added minus before the brackets here. So it is, after we multiplied equation number 1 by minus 1, we got that minus cosine theta equals to minus m squared plus d squared minus c squared over 2 times md. And we already found out that according to equation number 2, minus cosine theta equals to d squared plus n squared minus b squared over 2 times dn. In the next step, we created equation number 3 that states that minus cosine theta according to equation number 2, minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. So minus cosine theta according to equation number 1 equals to minus m squared plus d squared minus c squared over 2 times md. And it must be equal to minus cosine theta according to this equation number 2. And minus cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times dn. Okay? Then we multiply this equation number 3 by 2d. So in this side of the equation we have 2d over 2md. The 2d will get cancelled, 2d over 2d is 1, and in the denominator we left only with m. So in total this expression, after we multiplied by 2d, will be equal to minus m squared plus d squared minus c squared over m. Then we multiply this side of the equation by 2d. So here 2d over 2d is 1, so 2d will get cancelled, and we left in the denominator only with n. In total, in this side of the equation we have d squared plus n squared minus c squared over n. Then of course multiplied this equation number 3, and found out that according to equation number 3, minus n inside the brackets we have m squared plus d squared minus c squared equals to m inside the brackets we have d squared plus n squared minus b squared. Then we opened the brackets on both sides of the equation and found out that minus nm squared minus nd squared plus nc squared, because minus times minus is 1, equals to md squared plus mn squared minus md squared. Then we added to this equation number 3, nm squared. Nm squared minus nm squared is 0. We added nd squared minus nd squared is 0, and we subtracted nc squared. So nc squared minus nc squared is 0. So in this side of the equation we left with 0, with nothing. In the other side of the equation we have already md squared plus mn squared plus mb squared, and then here we added nm squared, so it is plus nm squared. We added nd squared, so it is plus nd squared, and we subtracted nc squared, so it is minus nc squared. Then we took this square, we took out this square as a common factor from md square and from nd square, so inside the brackets we left with m plus n. Then we took mn as a common factor from mn square and from nm square, so inside the brackets we left only with m plus n. And it is equal to minus mb square minus nc square equals to 0. We added mb square and nc square to this equation, equation number 3, and found out that this square times m plus n plus mn times m plus n equals to b square m plus c square n. Then we took out m plus n as a common factor from, we took out m plus n as a common factor from those two expressions. So inside the brackets we left with d square plus mn, and it is equal to b square m plus c square n. We already found out that m plus n is a, so we substitute m plus n by a, and finally we found out that a, this square m plus mn equals to b square m plus cn, or b square m plus c square n equals to a. Inside the brackets we have d square plus mn. This is exactly Stewart's theorem. Okay, then we proved Stewart's theorem according to so actually proved Stewart's theorem in two different methods. Okay, thank you very much.